Hello. Hi everyone. Next we are moving to the what is operation amplifier concepts. In that first topic is what is an op amp. You know the name itself op amp is nothing but a operational amplifier. It can be performed. It is an operational amplifier which can perform different operations like addition, subtraction, multiplication, division, integration, and differentiation, etc. So that means that only one IC it can be perform many operations. That's why it is called as a operational amplifier. This particular operation amplifier having a very high gain, as well as the input resistance is also high, output resistance is low. So so many advantages of this particular op amp we will discuss one by one. So after that, different uses of op amp, like scaling, just now I mentioned addition, subtraction, multiplication, division, etc. So it can be available in the different form, three different packages. So first one is a standard package, that is a DIL. DIL means just dual in line package. Second one is a TO5 package. So that is a very simple, that can be designed that particular way. And then third one, flat package. Third one, flat package. Okay, flat pack. These are the three different ways. Now operation amplifier, particular operation amplifier having in that single chip, having dozens of uh, dozens of transistors. In case of op amp, so many transistors, so dozens of transistors in a single chip. Dozens of resistors, dozens of capacitors. So you may get doubt, sir, it is internally capacitors or transistors, resistors are present. No, the IC can act as a resistor, that IC can act as a transistor, that IC can act as a capacitor. That means it is a speciality is there. Within the op amp single small chip, we can perform many operations. Okay, this is about the op amp. Next we are moving to the op amp symbol. Okay, next we are moving to the op amp symbol. In this particular diagram, these two diagrams is represented the op amp. So while you are seeing this particular op amp, how many terminals are present? Two input terminals, one output terminal. So we have a inverting terminal, non-inverting terminal, and then biasing voltage is present. So you may get the doubt, sir, this particular op amp only two input terminals, not more than that, only one output terminal, not more than. It is not like that. Op amp have a different configurations, maybe single input or more than one input, single output or more than one output also present, based on the different IC configuration. We'll see one by one. Okay, first one, this particular symbol, these particular symbols represented the first terminal. One is represented for non-inverting terminal. Non-inverting terminal. Next one, second terminal is represented as the inverting terminal. I'm sorry, negative sign. This negative sign represented the inverting terminal, and this positive, that is the second terminal, represented the non-inverting terminal. Non-inverting terminal. Next, this is called as a V1 and V2. After that, V0 is a output voltage. Output voltage. So this particular grounds is nothing but a biasing voltages in this particular case. So now this particular op amp have minimum 5 terminals. Just I mentioned already 3 terminals, right? Inverting terminal, non-inverting terminal, after that output terminal. The fourth one is a Everyone listen carefully because every point is important. You may expect 2 to 3 questions definitely from these integrated circuits. So positive bias supply voltage, just now I mentioned we have a biasing voltages. This is a plus VEE minus VEE. So positive bias voltage, positive bias supply. Second, next fifth terminal is a negative bias supply. Negative bias supply. Clear? So these are about the 5 terminals present in the op amp. All of it clear? Now we are moving to the polarity. Polarity conventions. In this case, the polarity conventions, just now we saw the op amp, these particular terminals. So let us discuss with help of that polarity conventions. So how the polarities will be there for this particular op amp. For example, in this particular case, this is a which terminal? Inverting terminal. This is a non-inverting terminal. For example, I grounded this particular terminal, that is a non-inverting terminal. Input is connected to the non-inverting terminal. Got my point? Okay. Non-inverting terminal is grounded, inverting terminal is connected to input. Output you may expected inverted the input, that means out of phase 180 degree. So if you are given the input is this particular sine wave, the output will be 180 degree, that is out of phase with the input, that is inverting. This particular input is inverted at the output, that's called it as an inverting amplifier. Got my point? So next one, the phase shifted. After that, I grounded inverting terminal, I connected to input here, right? Instead of connected input here, that okay. Again, I'm going to give the input signal is this particular signal, right? The output is same as the input, you will get the same signal as it is, but amplified is there. Amplification, that amplitude maybe increases because you are doing amplification. So what will happen? The phase, there is no phase difference. That is the input in phase with the output. So all of you got my point? In the both the cases, the first one, inverting case, for example, non-inverting case, non-inverting polarities, input and output. Okay, in case of inverting case, input as well as output both are in phase. In case of inverting case, input and output are inverted, so out of phase, so both are not in phase with each other. So this is about the polarity conventions related to the op amp. Everyone is clear about the polarity convention? We have an inverting input terminal, non-inverting input terminal. If you are connected the inverting input terminal to the input, the input is inverted as output. Output is inverted whenever you are connected to the inverted input terminals. Okay, non-inverting input terminal same as output. Output is same as input, only amplitude and magnitude are changes. We'll discuss further in this particular class. Very interesting examples I will provide. Okay, next we are moving to the ideal operation amplifier. Very important. You may expect one question from here. Okay, one question. Everyone listen carefully. Ideal operational amplifier. In this particular operation amplifier, we'll discuss the ideal operation amplifier without feedback. This is the operation amplifier, right? Any feedback is there in between input and output? There is no feedback. In that particular case, we are going to discuss the characteristics. So open loop, that is called as a open. This particular op amp is called as a open loop op amp. Okay, in this particular op amp we are following the we are going to discuss the characteristics. So first one is a open loop gain. Open loop gain, that is called as a AV. Open loop gain is infinity. What is open loop gain? Is infinity in the case of op amp, open loop op amp. That is the first characteristics. Second one, input resistance, that is a resistance between one and two terminal, that is a input resistance is infinity. Ideal case I am talking about. Okay, it is measured between the inverting and non-inverting terminals. So as well as third one, output resistance, that is a output terminal R0 is equal to 0. Okay, fourth one, infinity bandwidth. Infinity bandwidth. These are the four characteristics of a op amp. Of course, CMRR also infinity. So many characteristics we have. What is required, we will explain those things only. Based on these four characteristics, we have some additional advantages due to that. Okay, so additional advantages we are going to discuss now. Additional characteristics. Due to that additional characteristics, the first one, input, the input resistance is infinity, right? Whenever input resistance is infinity, what means the current flowing between these two terminals is 0. Got my point? Whenever input resistance is infinity, the current flowing between these two terminals is 0. It means that ideal op amp as a voltage controller, whenever it is control the current, it can be control the voltage, so it can act as a voltage controller. Okay, got my point? So every point is important in the examination. Next one, if R0 is equal to 0, that means that V0 not depending upon the load connected. V0 not depending upon the load connected, because it is offers very low resistance at the output depending upon load connected. Okay, next one, third important point here, op amp, the gain AV is equal to infinity. Okay, whenever it is infinity, it can be offered very high gain. For example, you will give the one, for example, the gain will be 10 power 6. For example, you are giving the some input here, the output will be 10 power 6 times. You may thinking that. Okay, I will explain the some logic here. For example, I will provide the input voltage is 1 volt. Okay, what you expected the output, it is a 10 to the power of 6 times the gain. For example, you may expect it as a output V0 is equal to 1 into 10 power 6 volt. Maybe practically it is possible, just it is practically impossible, right? How you make 1 volt to 10 power 6 volt? It is not possible, right? Some limitations are there. That's why I see here, in that particular case, even though gain is infinity or even though gain is very high 10 power 6, but some biasing voltage here connected. For example, it is a plus 15, it is minus 15. That means that whenever the input voltage is 1 volt, the gain, even though infinity, the output is limited to plus 15 to minus 15 only. Okay, those are the saturation. Okay, we are applying more than that, we are applying the gain more than that, you are expected, that is a saturation, the output is constant throughout the 15 volts only. Got my point? That is a way we are. Otherwise, in your studies also, you are thinking that gain is infinity or gain is very high, you are given the one input, you will get the more output 10 power 6 or 10 power 10 or 10 power 20. So why can't do that in the practically? Because of we are connecting the biasing terminals. Based on the biasing terminals, the output will be decided. We are expecting more output, but not more than the biasing terminals. Okay, fine. Next, we are moving to the another important topic, that is a virtual ground summing point. Virtual ground summing point. So first we will discuss about the summing point. What is mean by summing point? The point at which current will be divided. For example, this point A, the current, the junction A A can just see that current, apply the current division rule, KCL. Sum of incoming currents I1 is equal to sum of outgoing currents I2. Okay, so this is a summing point. This particular point is called as a summing point. This is the feedback path. Feedback path, that is a input to output is connected. This is a R1 is input resistance, and V1 is a in a inverting terminal, V2 is a non-inverting terminal. Here non-inverting terminal, V0 is output. Okay, this is about the summing point. Come back to the virtual ground. Virtual ground, the name itself, virtually grounded, not physically grounded. How it is see? Just now I mentioned the current flowing through the op amp, the current flowing through the op amp is equal to 0 or not. Whenever current flowing through the op amp is 0, that means that whenever you are given some current I1, the same current flowing through the I2, both the currents are equal, because there is no current flowing through the op amp. So there is no current flowing through the op amp. What is the potential available here? 0 volt, because it is grounded. Now this current will be 0. The current between these two terminals will be 0. Whenever it is possible, the two terminal current will be 0. Potential is 0. Potential is same. Here potential is 0 volt. You may expect the potential is 0 volt here. Okay, whenever it is 0 volt and 0 volt, there is no potential difference, there is no current flowing, then satisfy our condition. So virtual ground means that the ground potential is appears as a, for example, plus terminal is grounded, the same potential appears as a inverting terminal. That means here VA is equal to 0. Okay, got my point everyone? Virtual ground means the one of the terminal is non-inverting terminal is grounded, the same voltage is appears under the inverting terminal also, due to the current flowing through the op amp is equal to 0. That is the ideal characteristics. Due to that, virtual ground, both the voltages are 0. Okay, next I will discuss further why it is the point here Vi is reduced almost 0. Why? What is the reason they are asking? So we'll see two cases. The first case already discussed, due to the virtual ground, because there is no current flowing through the op amp, the potential difference is same. So ground potential is same as the input potential, terminal potential. Okay, that is the first case. Second case, in this particular op amp, for example, it is a inverting operation amplifier. Okay, let me take C here. The first case, virtual ground concept, due to that Vi is almost reduced to 0. Next, second one is a V0. Some of the output is feedback to the input. For example, it is inverting amplifier. For example, you will give in the 5 volt, right? So output may be amplified, and then some part of the input is connected back to the output is connected back to the input. That means that, for example, the input voltage is same as output voltage. So this output voltage feedback to the input as inverted. So it is a minus. Once it is inverted, you will get 0. That means that some part of the output back to input through feedback. So input is equivalent to output. That particular case, the Vi is reduced to 0. That is another chance is there. Okay, these are the two cases. Vi is reduced to almost 0. Okay, so that is enough for discussion. Now we are moving to the op amp applications. Very, very important. So op amp having in this particular case, in our syllabus it is mentioned, based on that 7 applications I am going to mention. The first application is a scalar or linear constant gain. Scalar or linear constant gain. Okay, that is the first one. So in that we are going to discuss about the inverting, and second one is non-inverting cases. Both the cases we are going to discuss. Second application here, unity follower. Third one, adder. or summer. Fourth one, subtractor. Fifth one, integrator. Sixth one, differentiator. Seventh one, comparator. Okay, we'll discuss all this. So first we'll start with the linear amplifier. Okay, this linear amplifier having two amplifiers, inverting amplifier or negative scale amplifier. Inverting amplifier. Next, second one is non-inverting amplifier. So we'll discuss one by one inverting amplifier. So inverting amplifier means non-inverting terminal is connected to ground and inverting terminal connected to input terminal. This input terminal is out of phase. The input voltage is inverted and appears at the output terminals. So mathematically I will prove that inverting amplifier, the input is inverted present at the output terminal. So how it is mathematical I will prove in this particular case. So in the particular, what I gave the particular formula at the end, it is very very important. You can note down that formula. So here in that particular case, just now I mentioned in case of op amp, what about the current flowing through the op amp is equal to 0. Whenever current flowing through the op amp is equal to 0, apply KCL at node A. Apply KCL at node A. Whenever apply the KCL at node A, the current I1 is incoming current, right? Next, here this current will be 0. I2 is the outgoing current. That means I1 is equal to I2. You know, this I1 is coming from V1 to, for example, here VA. Okay, one more point. What about VA? You know, virtual ground concept, just now we discussed. Virtual ground means that here appears as a 0 volt. Due to current will be 0 through the op amp, that means that what is the potential available? 0. Whenever the potential available is 0, what about the VA? The same terminal connected 0. Due to the virtual ground concept, VA is equal to 0. Now current will be flowing from V1 to 0 volt side, higher potential to lower potential, that is mentioned there. So V1 minus 0 divided by R1 is equal to I2 current direction from 0 to V0. This is the current direction. But you know, current always flowing from the highest potential to lowest potential. Actually the current direction, this is the current direction, because output voltage is obviously more than the 0 volt, yes or no? But our mentioned direction is from the A to output terminal. That's why I mentioned here 0 minus V0 divided by RF. Okay, everyone is clear about that? Now we are going to simplify further. V0 by V1 or Vin. V0 by Vin is equal to now minus RF divided by R1 or R input. This is the formula for inverting amplifier. Okay. So in case of inverting amplifier, V0 by Vin is equal to minus RF by R1 or R input. That is for inverting amplifier. Now the case here, negative sign shows that the input is inverted and appears at the output. That is a conclusion. Okay. Next we are moving to the non-inverting amplifier. In case of non-inverting amplifier, also called it as a positive scalar. In the examination, write the formula for positive scalar. Maybe it is out of the syllabus. You are thinking that no. The another name for inverting amplifier is a positive scalar. Now here grounded the which terminal? Inverting terminal is grounded. Non-inverting terminal connected to the input. You may expect it at the input in phase with the output. Now apply KCL at node A. Apply KCL at node A. Whenever you apply the KCL at node A, actually you know what is the input voltage V2, right? According to virtual ground concept, what amount of voltage V2, or for example I will consider Vin. So the Vin is same as here Vin. Otherwise you can notate it as a V2 also, no issue. Okay, so I can mention V2. So this potential is nothing but a V2 according to virtual ground concept. Now we can voltage here 0, of course it is V0. Apply KCL at node A. What is incoming current? I. The current flowing here is 0, ideal case. So incoming current I is equal to outgoing current is also I, because both the currents are same. Now this particular current is flowing from V2 to 0 volt. That means V2 minus 0 divided by R1 is equal to, in this particular case, V0 to V2. That is a V0 minus V2 by R. Got my point? Now V2 by R1, this particular side, plus V2 by RF is equal to V0 by RF. So from that I can take the LCM. R1 RF is equal to R1 plus RF is equal to V0 by RF. Now this particular RF get cancelled. So V0 by V2, that is the output, will be equivalent to R1 plus RF divided by R1. That means 1 plus RF divided by R1. This is a important formula. So finally, what is a V0? V0 is equal to 1 plus RF divided by R1 into V2. This is the formula of a non-inverting case. So very important. You will expect one question from this particular inverting non-inverting case. Maybe problem or this particular formula they might be asked. Okay. Next we are going to the next topic, problems we are going to discuss. The first problem here, for inverting amplifier, R1 is, so inverting amplifier, you know already, this is the output, negative and positive, it is inverting and non-inverting input terminals. Okay, this is RF, this is R1. What is saying that R1 is 1 kilo ohm, RF is a 1 mega ohm. Assuming that ideal op amp. Okay, determine the following circuit values. Okay, determine the following circuit values. The first one is a voltage gain. What is a voltage gain? The voltage gain formula AV is equal to minus RF divided by, it is inverting amplifier, right? Minus RF divided by R1. RF is a 1 mega ohm divided by 1 kilo ohm. So finally we will get minus 1000 is a gain. So next, input resistance. Because it is a ideal op amp, R1 is 1 kilo. Already it is mentioned, R1 is equal to 1 kilo ohm. That is the input resistance. What is the output resistance? Output resistance, whenever it is an ideal op amp, output resistance is equal to 0. Okay, output resistance is equal to 0. So this is about the example. Just we are moving to the next topic, unity follower. Okay, so unity follower is very simple. This is a non-inverting amplifier. Just replace the feedback resistor. Here RF is there, RF make it as a 0. Just now you know particular inverting amplifier formula V0 is equal to 1 plus non-inverting amplifier RF divided by R1 into V2 or Vin, input voltage. Got my point? Now this RF is equal to 0. So whenever RF is equal to 0, 1 plus 0 by R1 into Vin. Finally, you know, this becomes 0, 1 into Vin. V0 is equal to Vn. What is mean by voltage follower? The input voltage is same as output voltage. That is called as a voltage follower. Got my point? What is mean by voltage follower? input voltage is same as the output voltage, that is called as a voltage follower. That is a unity follower also called as a. Okay, everyone is clear about the unity follower. They will give this particular circuit, identify which is a circuit name. Maybe inverting amplifier, non-inverting amplifier, unity follower, none of the above. You can identify that is a unity follower. Next we are moving to the adder or sum, that is a summation. So this particular diagram we are going to discuss that. So here how many inputs are there? V1, V2 and V3 output, and then again same thing, apply KCL at node A. Apply KCL at node A. So whenever apply KCL at node A, this is the ideal operation amplifier, current will be 0 according to virtual ground concept. This is a 0 volt. Obviously the voltage at VA is equal to 0. Now the current, the values are V1, 3 currents, right? I1 plus I2 plus I3 is equal to I. Okay, what is I1? V1 minus 0 by R1 plus V1 minus 0, V2 minus 0 by R2 plus V3 minus 0 by R3 is equal to output 0 minus V0 divided by Rf. Okay, so now we can take we can consider R1 is equal to R2 is equal to R3 is equal to Rf. Okay, all are same, equal resistors. Then you will get V0 is equal to V1 plus V2 plus V3. That means that the input voltage is sum of the output voltages. Otherwise, in general, Rf, R1, R2, R3 are not equal. The output voltage is equal to 1 by R1 into V1 plus. Okay. Now, for example, both are not equal. R1, R2, R3 is equal to R not Rf. In that particular case, V0 is equal to 1 by, that is a Rf divided by R1 into V1 plus Rf divided by R2 divided by V2 plus Rf divided by R3 into V3. So this is a minus of. Okay, so this is about the summing amplifier. In that particular case, now we can consider this is a K1 constant, this is a K2, and then this is a K3. Okay, finally got the idea. What is the summing amplifier output? V0 is equal to V1 plus V2 plus V3. The summation of all inputs with some constant. K1, K2 and K3 are the constants. So we'll look at the one problem, we'll get the idea about exactly what is the summing amplifier later, once we completed the subtractor. Once next we are moving to the subtractor, then we are going to the example problem based on that. Okay, all of you following, all of you enjoy the class, right? Subtractor. So subtractor, the name itself, the difference. So how it is, we'll see. The first case, here V1 and V2. That means that how many inputs are connected directly? 2 inputs at a time you are connected. You want to find out the output. Apply the superposition theorem. So, in the superposition theorem, just now we can apply at a time only one input. Another output is a deactivated. For example, I am going to use V1. V2 is a deactivated. That means that it is grounded. So, then it is called as a which amplifier here? This amplifier is an inverting amplifier. So what is the output? V0 is equal to, just now we know inverting amplifier, minus Rf divided by R1. V0 prime is equal to minus Rf divided by R1 into V1. Okay, that is the first equation. Next, apply the KCL at, apply superposition in the same case. V1 is deactivated and V2 is connected to ground. V2 is connected to the input. In that particular case, that is a non-inverting amplifier, that is a V0 double prime is equal to 1 plus Rf divided by R1 into V1. Okay, this is the second case. Now we can add it both are V1 minus V2. V2. That is a V output. This is a difference amplifier, right? Finally, V0 is equal to the difference of both. That will be minus 1 plus Rf divided by R1 into V2 minus, this particular case it is a V2 because input voltage is V2, right? V2 minus Rf divided by R1 into V1. Okay, got my point. Now in this particular case, Rf, in this particular case, R1 is very greater than Rf. R1 is very greater than Rf is very greater than R1. That means that we can neglect this particular portion. We'll get some Rf divided by R1 is very more than the R1. That's why we can neglect this particular one, V2 minus V1. So this is the differential. What is the condition here to neglect this particular one? Rf, this particular feedback resistor, is very greater than Rf. That means Rf by R1 very greater than 1. We can neglect this particular one, that is called. So finally, Rf is equal to R1. Finally, V0 is equal to difference of input, V2 minus V1. Okay, that is about explanation of subtractor. Okay, next we are moving to the example problem. In the subtractor circuit shown in the figure, just now we saw R1 is a 5K, R2 is a 10K, V1 is a 4 volt, V2 is a 5 volt. Find the output voltage. Subtractor formula, 1 plus Rf divided by R1 V2 minus Rf divided by R1, that is a V1. 1 plus, what is Rf? 10K by 5K into V2 5 volt minus Rf 10K divided by R1 5K into V1 4 volt. So finally we'll get here plus 7 volt is the output. So that way you need to find out. We remember that some formulas, in case of examination numerical question, 40% numerical, 40 to 50% numerical questions also there. So you can go through the formulas once before going to the exam. Definitely can remember all these formulas. Next we are moving to the last 3 topics, that is the integrator, differentiator and comparator. Then we'll end this particular topic. So integrator, the integrator is doing that whenever input signal is connected to the integrator, the output is integrated of the input. Okay, this is a constant signal you are connected, it is a convert into linear signal. So this particular op amp, how to construct the integrator, this is the condition. So integrator, just capacitor, in place of RF you are connected the capacitor, it is converted as the integrator. Okay, that is a symbol you need to remember. So we'll derive exactly this integrator or not, we'll derive the equations. Okay, mathematically we can prove that is integrator equations. So this current will be 0. That means that I1, the current will be 0 here. The current will be 0 here. That means that I1 is the same as I2. Apply KCL at that particular node. I1 is equal to I2. Whenever both the currents are equal, just apply the normal nodal analysis condition. V1 minus 0, that is a V1 minus 0 by R1 is equal to, in case of capacitor, in the Laplace transformation technique, Laplace transformation concept, minus S into CV, we can also write it as a, okay, so minus SC V0, that is a Laplace convention. So based on that gain AV, so V0 divided by V in or V1 is equal to minus 1 by SCR, this is a gain. In case of integrator is there, we can use this particular formula. Otherwise, in case of time domain, V0 is equal to 1 by RC or CR integration of V of t into dt. So this is a output voltage you may expected in the input. That means that output is integrated of input with the help of the one constant 1 by RC. Okay, so this is about the integrator. Next we are moving to the differentiator. So before moving to the differentiator, we'll look at the one problem related to the integrator. So in that particular case, the 5 millivolt 1 kHz sinusoidal signal applied to the input of op amp as integrator for 100k and C1 is 1 microfarad. Find the output voltage. We know the formula for output voltage V naught of T is equal to integration, that is a minus 1 by RC integration of input voltage into dt. Here correct yourself, it is a minus. Already here minus is there, na? That is a minus. Now substitute all the values. So minus 1 by RC. R value is 100k into 1 micro. Integration of input voltage. So input is a 0 to t 5 millivolt sine wave. It is a 5 sine omega t. So omega is equal to 2 pi f. 2 pi f is a 1 kilohertz, that is a 1000. So that means that 2000 pi. Okay, 2000 pi. So 1 by this particular RC minus 10, 0 to 5, as well as 5 sine Vm sine omega t, right? 5 sine 2000 pi t. So after we just apply the integration here, minus 50, that 5 outside, integration of sine minus cos 2000 pi by 2000, limits are 0 to t. After apply the limits, you will get 1 by 40 pi cos 2000 pi t minus 1. Pi t minus 1. This is about the output. Okay, next we are moving to the differentiator. Okay, in case of differentiator, the input is differentiated at present at the output. For example, your linear signal is converted, it is converted into constant signal. Differentiation of ramp signal, it is a constant signal. So see here, just interchange the resistance and capacitance, you will get the differentiator. Again here current will be 0. What about the current now? Current I is equal to, this particular current I is equal to C into dV by dt. dV, that is a dVc by dt or dV by dt. This is a capacitor current. This current is same as both the currents are same, right? So this current is also now I is equal to minus I into R. V is equal to minus I into R. V naught is equal to minus I into R. What is the I value? I is equal to minus C dVc by dt into R. This is the output is derivative of input. Output is derivative of input voltage you are connected. So this is about the differentiator. Got my point? Differentiation is nothing but a output is differentiation of input. Maybe here V1, you can also take it as a V1, no issue. Output is a differentiation of input. So this is about the differential. Last topic. Next we are moving to the comparator. So comparator, it is nothing but a compare the two input signal. Let us see. We have a two inputs V1 and V2. For example, V1 and V2 both are equal. What is the difference is 0. That means that there is no effect of the output. Okay, V0 is equal to 0. But in case of V1 and V2 are not equal, the small difference For example, it is a small difference. This particular amplifier is amplifies and output is APS at the output. That means that very small change we can compare the signal and present at the output. That is a call it as a detector, comparator or detector. It detect the or comparison between the input and output. That's why it is called as a comparator. So we have some amplifier gain A is present. So this is a circuit we are call it as a comparator. In the examination, they will provide this particular circuit. V1, V2, V1 is not connected to ground, V2 is not connected to ground. Both are connected to the input. It can act as a comparator. So that's what we are end of this particular lecture according to your syllabus. Next, we left with the one topic, that is fabrication in this particular lecture. That is the lecture number 1. So I'm going to update that one also. So just we finish the integrated circuit. Thank you.